Hello, welcome back to our course. So in the previous course, we have learned the introduction of E-MapReduce and demonstrated the use of Hadoop and Hive on EMR. In this course, we learn a new big data processing technology, Spark. As a member of Hadoop ecosystem and supported by EMR, it is widely used in various kinds of computing. Let's first look at today's learning goals. Upon completion of this course, you will be able to know what Spark is, know the advantages of Spark, understand how to use Spark on E-MapReduce, understand the features of Spark RDB, know what Spark dataset and Spark data frame are, understand the functions of Spark streaming, know what Spark dstream is. Are you ready? Let's start today's course. First of all, what is Spark? Apache Spark is a fast and general-purpose cluster computing system. It provides high-level APIs in Java, Scala, Python, and R, and an optimized engine that supports general execution graphs. It also supports a rich set of higher-level tools, including Spark SQL for SQL and structured data processing, MMlib for machine learning, GraphX for graph processing, and Spark streaming. The Hadoop yarn-based architecture provides the foundation that enables Spark and other applications to share a common cluster and dataset while ensuring consistent levels of service and response. Spark is now one of many data access engines that work with Yarn in HCP. Spark has many application components. Spark Core is the foundation of the platform. It is responsible for memory management, fault recovery, scheduling, distributing and monitoring jobs, and interacting with storage system. Spark Core is exposed through an application programming interface built for Java, Scala, Python, and R. These APIs hide the complexity of distributed processing behind simple, high-level operators. Spark includes MLlib, a library of algorithms to do machine learning on data at scale. Machine learning models can be trained by data scientists with R or Python on any Hadoop data source, saved using MLlib, and imported into a Java or Scala-based pipeline. Spark was designed for fast, interactive computation that runs in memory, enabling machine learning to run quickly. The algorithms include the ability to do classification, regression, clustering, collaborative filtering, and pattern mining. Spark Streaming is a real-time solution that leverages Spark Core's fast scheduling capability to do streaming analytics. It ingests data in mini-batches and enables analytics on that data with the same application code written for batch analytics. This improves developer productivity because they can use the same code for batch processing and for real-time streaming applications. Spark Streaming supports data from Twitter, Kafka, Flume, HDFS, and ZeroMQ, and many other found from the Spark packages ecosystem. Spark SQL is a distributed query engine that provides low latency, interactive queries up to 100 times faster than MapReduce. It includes a cost-based optimizer, columnar storage, and code generation for faster queries, while scaling to thousands of nodes. Business analysts can use standard SQL or the Hive query language for querying data. Developers can use APIs available in Scala, Java, Python, and R. It supports various data sources out of the box, including JDBC, ODBC, JSON, HDFS, Hive, ORC, and Parquet. Other popular stores: Amazon Redshift, Amazon S3, Couchbase, Cassandra, MongoDB, Salesforce.com, Elasticsearch, and many others can be found from the Spark packages ecosystem. Spark GraphX is a distributed graph processing framework built on top of Spark. GraphX provides ETL, exploratory analysis, and interactive graph computation to enable users to interactively build and transform a graph data structure at scale. It comes with a highly flexible API and a selection of distributed graph algorithms. There are many benefits of Apache Spark to make it one of the most active projects in the Hadoop ecosystem. These include speed. Engineered from the bottom up for performance, Spark can run fast analytic queries against data of any size. Spark can be 100 times faster than Hadoop for large-scale data processing by exploiting in-memory computing and other optimizations. Spark is also fast when data is stored on disk and currently holds the world record for large-scale on-disk sorting. Ease of use. Spark has easy-to-use APIs for operating on large datasets. This includes a collection of over 100 operators for transforming data and familiar data frame APIs for manipulating semi-structured data. Apache Spark natively supports Java, Scala, R, and Python, giving you a variety of language for building your applications. These APIs makes it easy for your developers because they hide the complexity of distributed processing behind simple, high-level operators that dramatically lowers the amount of code required. A unified engine. Spark comes packaged with higher-level libraries, including support for SQL queries, streaming data, machine learning, and graph processing. These standard libraries increase developers' productivity and can be seamlessly combined to create complex workflow. Next, I will show you how to use Spark in EMR. I will use Spark to execute Python's word counting program. Select Object Storage Service to go to the OSS console. Click a bucket. Click Files. Create a folder and upload the input file. then upload program. Open your E-MapReduce console. Click New Job. Input job name and description. Choose job type as Spark. Click OK. Click Insert an OSS URI. Choose the Python program. Choose Input File and specify the output path. Click Design Workflow. Click New Workflow. Input workflow name and description. Design a workflow with start and end nodes. Choose the Spark job we designed. Click OK. Click Run. Waiting for execution state to become OK. Look at the output file on OSS. Download the file. You can see the results of word counting in it. Overview of Spark Basics. Spark revolves around the concept of a resilient distributed dataset, which is a fault-tolerant collection of elements that can be operated on in parallel. There are two ways to create RDDs: parallelizing an existing collection in your driver program, or referencing a dataset in an external storage system, such as a shared file system, HDFS, HBase, or any data source offering a Hadoop input format. Internally, each RDD is characterized by 5 main properties. a list of partitions, a function for computing each split, a list of dependencies on other RDDs. Optionally, a partitioner for key-value RDDs. Optionally, a list of preferred locations to compute each split. All of the scheduling and execution in Spark is done based on these methods, allowing each RDD to implement its own way of computing itself. Several features of Apache Spark RDD are: first, in-memory computation. Spark RDD has a provision of in-memory computation. It stores intermediate results in distributed memory instead of stable storage. Second, lazy evaluations. All transformations in Apache Spark are lazy, in that they do not compute their results right away. Instead, they just remember the transformations applied to some base dataset. Spark computes transformation when an action requires a result for the driver program. Third, fault tolerance. Spark RDDs are fault tolerant as they track data lineage information to rebuild lost data automatically on failure. They rebuild lost data on failure using lineage. Each RDD remembers how it was created from other datasets to recreate itself. Fourth, immutability. Since RDDs are immutable, which means unchangeable over time, that property helps to maintain consistency when we perform further computations. As we cannot make any change in RDD once created, it can only get transformed into new RDD. This is possible through its transformation processes. Fifth, partitioning. Partitioning is the fundamental unit of parallelism in Spark RDD. For example, reading data files on HDFS produces the same number of RDD partitions as blocks. Each partition is one logical division of data, which is mutable. One can create a partition through some transformations on existing partitions. 6. Persistence. Users can state which RDDs they will reuse and choose a storage strategy for them. 7. Coarse-grained operations. It applies to all elements in datasets through maps or filter or group by operation. 8. Location stickiness. RDDs are capable of defining placement preference to compute partitions. Placement preference refers to information about the location of RDD. The DAG scheduler places the partitions in such a way that task is close to data as much as possible. Thus, speed up computation. RDDs support two types of operations: transformations, which create a new dataset from an existing one, and actions, which return a value to the driver program after running a computation on the dataset. For example, map is a transformation that passes each dataset element through a function and returns a new RDD representing the result. On the other hand, reduce is an action that aggregates all the elements of the RDD using some function and returns the final result to the driver program. All transformations in Spark are lazy. in that they do not compute their results right away. Instead, they just remember the transformations applied to some base dataset. The transformations are only computed when an action requires a result to be returned to the driver program. This design enables Spark to run more efficiently. For example, we can realize that a dataset created through map will be used in a reduce and return only the result of the reduce to the driver, rather than the larger mapped dataset. By default, each transformed RDD may be recomputed each time you run an action on it. However, you may also persist an RDD in memory using the persist method, in which case Spark will keep the elements around on the cluster for much faster access the next time you query it. There is also support for persisting RDDs on disk or replicated across multiple nodes. There are two types of transformations. Narrow transformation. In narrow transformation, all the elements that are required to compute the wrappers in single partition live in a single partition of parent RDD. A limited subset of partition is used to calculate the result. Narrow transformations are the result of map and filter. Wide transformation. In wide transformation, all the elements that are required to compute the records in a single partition may live in many partitions of parent RDD. Wide transformations are the result of group by key and reduce by key, and wide transformation requires data shuffling that shows its results in stage boundaries. The shuffle in Spark's mechanism for redistributing data so that it's grouped differently across partitions. This typically involves copying data across executors and machines, making the shuffle a complex and costly operation. While we create a new RDD from an existing Spark RDD, that new RDD also carries a pointer to the parent RDD in Spark. That is the same as all the dependencies between the RDDs. Those are logged in a graph, rather than the actual data. It is what we call a lineage graph. RDD lineage is nothing but the graph of all the parent RDDs of an RDD. We also call it an RDD operator graph or RDD dependency graph. The dependence relationship between RDDs for performing wide transformation is wide dependency. Otherwise, it's narrow dependency. RDD splits into the partition, and each node operates on a partition at any point in time. Here, the series of Scala function executes on a partition of the RDD. These operations compose together, and Spark execution engine view these as DAG, directed acyclic graph. It is a scheduling layer in a Spark which implements stage-oriented scheduling. It converts logical execution plan to a physical execution plan. When an action is called, Spark directly strikes to DAG scheduler. It executes the tasks those are submitted to the scheduler. Spark uses pipeline operations to optimize its work. That process combined the transformations into a single stage. The basic concept of DAG scheduler is to maintain jobs and stages. It tracks through internal registries and counters. There are following steps through DAG scheduler works. It completes the computation and execution of stages for a job. It also keeps track of RDDs and run jobs in minimum time and assigns jobs to the task scheduler. Task scheduler means submitting tasks for execution. It determines the preferred location on which we can run each task respectively. It is possible with a task scheduler that gets the information of current cache status. It handles the track of RDDs which are cached to avoid recomputing. In this way, it also handles failure. As it remembers at what stages it already produced output files, it hails the loss. Due to shuffle output files may loss, so it helps to recover failure. This picture describes the execution of DAG. There are dependencies among various RDDs. These dependencies from DAG. DAG scheduler classifies the DAG formed by these dependencies. The rule of division are very simple. Back-to-back, narrow dependencies are added to this stage, and wide dependencies are used to classify the DAG. The division of stage has been completed. DAG scheduler generates task set based on each stage and submits task set to task scheduler. Task scheduler is responsible for specific task scheduling and finally starts task on worker. One of the most important capabilities in Spark is persisting a dataset in memory across operations. When you persist an RDD, each node stores any partitions of it that it computes in memory and reuses them in other actions on that dataset. In this way, for a scenario where multiple operations are performed repeatedly for an RDD, only one RDD calculation is needed, and then the RDD is used directly instead of repeatedly calculating the RDD. Caching is a key tool for iterative algorithms and fast interactive use. Skillfully used RDD persistence, even in some scenarios, can improve the performance of Spark application by 10 times. RDD persistence is very important for iterative algorithms and fast interactive applications. You can mark an RDD to be persisted using the persist or cache method on it. The first time it is computed in an action, it will be kept in memory on the nodes. Spark's cache is fault-tolerant. If any partition of an RDD is lost, it will automatically be recomputed using the transformation that originally created it. The difference between cache and persist is that cache is a simplified way of persist. The bottom layer of cache is the parametric version of persist called, and at the same time it is called persist. Memory only to persist data into memory. If you need to remove the cache from memory, you can use the unpersist method. In addition, each persisted RDD can be stored using a different storage level. For example, to persist the dataset on disk, persist it in memory, but as serialized Java objects. The cache method is a shorthand for using the default storage level, memory only. And persist method supports multiple storage levels as listed in the right figure. Spark SQL. Spark SQL is a Spark module for structured data processing. Unlike the basic Spark RDD API, the interfaces provided by Spark SQL provide Spark with more information about the structure of both the data and the computation being performed. Internally, Spark SQL uses this extra information to perform extra optimizations. There are several ways to interact with Spark SQL, including SQL and the Dataset API. When computing a result, the same execution engine is used, independent of which API language you are using to express the computation. This unification means that developers can easily switch back and forth between different APIs based on which provides the most natural way to express a given transformation. Spark SQL offers three main capabilities for using structured and semi-structured data. They are following below. Spark SQL provides a data frame abstraction in Python, Java, and Scala. It simplifies working with structured data sets. In Spark, SQL data frames are same as tables in a relational database. Spark SQL can read and write data in various structured formats, such as JSON, Hive tables, and Parquet. By using SQL, we can query the data, both inside a Spark program and from external tools that connect to Spark SQL. Both data frames and data sets are distributed collections of data. They support Spark SQL operations including DSL and SQL. The predecessor of data frame is Schema RDD, which has been renamed data frame since Spark 1.3.0. The main difference from Schema RDD is that data frame no longer directly inherits from RDD, but implements most of the functions of RDD itself. You can still invoke the RDD method on the data frame to convert it to an RDD. Data frames are data sets, which is ideally organized into named columns. We can construct a data frame from an array of different sources, like structured data files, Hive tables, external databases, or existing RDDs. Data frames are equal to a table in a relational database or a data frame in R Python with good optimizations. Data frame is used for processing of a large amount of structured data. Basically, it contains rows with a schema. Moreover, that schema is nothing but an illustration of the structure of data. It is more powerful than RDD, but it attains features of RDD as well. There are several features. Those are common to RDD, such as distributed computing capability, immutability, in-memory, resilience. Also provides higher-level abstraction. Generally, it allows users to impose the structure onto a distributed data collection. There are also some limitations of data frames in Spark SQL, like in SQL data frame, there is no compile time type safety. Hence, as the structure is unknown, manipulation of data is not possible. We can convert domain object into data frame, but once we do it, then we cannot regenerate the domain object. Dataset is a new interface added in Spark 1.6. A dataset can be constructed from GVM objects and then manipulated using functional transformations. In Spark 2.0, data frame is represented by a dataset of rows. As we know, there were some drawbacks with RDD as well as Spark data frames. To overcome those limitations datasets introduced. As in data frame, data cannot be manipulated without knowing its structure. Since there were no clause for compile time type safety. While in RDD, there was no automatic optimization. Thus, whenever required, we need to do it manually. To overcome this issue, we need a dataset. As shown in the case on the right, RDD just divides data into rows, but data frame adds structured parameters when dividing, while dataset manages each field of each row in a more ingenious way. So datasets inherit all the features of RDD and data frame, such as RDD's convenience, data frame's performance optimization, Scala's static type safety. If low-level functionality is there. Also, if high-level abstraction is required, you can use data frame. Dataset is used for high-degree safety at runtime. To take advantage of typed GVM objects. Also, take advantage of the catalyst optimizer. To save space. It required faster execution. Spark Streaming Programming. Spark Streaming is an extension of the core Spark API that enables scalable, high-throughput, fault-tolerant scheme processing of live data streams. Data can be ingested from many sources like Kafka, Flume, or TCP sockets, and can be processed using complex algorithms expressed with high-level functions like map, reduce, join, and window. Finally, processed data can be pushed out to file systems, databases, and live dashboards. In fact, you can apply Spark's machine learning and graph processing algorithms on data streams. Internally, it works as follows. Spark Streaming receives live input data streams and divides the data into batches, which are then processed by the Spark engine to generate the final stream of result in batches. Spark streaming provides a high-level abstraction called discretized stream or D-stream, which represents a continuous stream of data. These streams can be created either from input data streams from sources such as Kafka, Flume, and Kinesis, or by applying high-level operations on other D streams. Internally, a D stream is represented as a sequence of RDDs. Next, we elaborate on the basics of Spark streaming. Discretized stream, or D-stream, is the basic abstraction provided by Spark streaming. It represents a continuous stream of data, either the input data stream received from source or the processed data stream generated by transforming the input stream. Internally, a D-stream is represented by a continuous series of RDDs, which is Spark's abstraction of an immutable distributed dataset. Each RDD is a D-stream contains data from a certain interval, as shown in the following figure. Any operation applied on a D-stream translated to operations on the underlying RDD. These underlying RDD transformations are computed by the Spark engine. The D-stream operation hide most of these details and provide the developer with a higher-level API for convenience. Spark streaming is a Spark-based streaming batch engine. Its basic principle is to process input data in batches at a certain time interval. When the batch interval is reduced to second level, it can be used to process real-time data streams. Spark D-stream supports two types of operations. Transformations. Similar to that of RDD, transformations allow the data from the input D-stream to be modified. D-streams support many of the transformations available on normal Spark RDDs. The transform operation, along with its variations like transform with, allow arbitrary RDD to RDD functions to be applied on a D-stream. It can be used to apply any RDD operation that is not exposed in the D-stream API. For example, the functionality of joining every batch in a data stream with another dataset is not directly exposed in the D-stream API. However, you can easily use transform to do this. This enables very powerful possibilities. For example, one can do real-time data cleaning by joining the input data stream with pre-computed spam information, maybe generated with Spark as well, and then filtering based on it. Output operations. Output operations allow D-streams data to be pushed out to external systems like a database or a file system. Since the output operations actually allow the transformed data to be consumed by external systems, they trigger the actual execution of all the D-stream transformations, similar to actions for RDDs. A streaming application must operate 24 hours 7 days, and hence must be resilient to failures unrelated to the application logic. For this to be possible, Spark streaming needs to checkpoint enough information to a fault-tolerant storage system, such that each can recover from failures. There are two types of data that are checkpointed: metadata checkpointing, data checkpointing. Metadata checkpointing is primarily needed for recovery from driver failures, whereas data or RDD checkpointing is necessary even for basic functioning if stateful transformations are used. When to enable checkpointing, checkpointing must be enabled for applications with any of the following requirements. First, usage of stateful transformation. If either update state by key or reduce by key and window is used in the application, then the checkpoint directory must be provided to allow for periodic RDD checkpointing. Recovering from failures of the driver running the application. Metadata checkpoints are used to recover with progress information. Note that simple streaming applications without the aforementioned stateful transformation can be run without enabling checkpointing. The recovery from driver failures will also be partial in that case. Some received but unprocessed data may be lost. How to configure checkpointing? Checkpointing can be enabled by setting a directory in a fault-tolerant, reliable file system to which the checkpoint information will be saved. This is done by using checkpoint method. This will allow you to use the aforementioned stateful transformations. Additionally, if you want to make the application recover from driver failures, you should rewrite your streaming application to have the following behavior. When the program is being started for the first time, it will create a new streaming context, set up all the streams, and then call start. When the program is being restarted after failure, it will recreate a streaming context from the checkpoint data in the checkpoint directory. Note that checkpointing of RDDs incurs the cost of saving to reliable storage. This may cause an increase in the processing time of those batches where RDDs get checkpointed. Hence, the interval of checkpointing needs to be set carefully. At small batch sizes, the checkpointing every batch may significantly reduce operation throughput. Conversely, checkpointing too infrequently causes the lineage and task sizes to grow, which may have detrimental effects. Spark streaming also provides windowed computations, which allow you to apply transformations over a sliding window of data. The following figure illustrates this sliding window. As shown in the figure, every time the window slides over a source D stream, the source RDDs that fall within the window are combined and operated upon to produce the RDDs of the windowed D stream. In this specific case, the operation is applied over the last 3 time units of data and sliced by 2 time units. This shows that any window operation needs to specify 2 parameters: window length, the duration of the window; sliding interval, the interval at which the window operation is performed. These 2 parameters must be multiple of the batch interval of the source D stream. If the window length is larger than the sliding interval, repeated calculations will occur. If the window length is smaller than the sliding interval, some data will be lost. In this course, we mainly learn what Spark is and how Spark is used on E-MapReduce. Next, review the key points of this lesson. First, you need to understand what Spark is. Apache Spark is a fast and general-purpose cluster computing system. It provides high-level APIs in Java, Scala, Python, and R, and an optimized engine that supports general execution graphs. It also supports a rich set of higher-level tools, including Spark SQL for SQL, and structured data processing, MLlib for machine learning, GraphX for graph processing, and Spark Streaming for real-time analytics. It can be 100 times faster than Hadoop for large-scale data processing by exploiting in-memory computing and other optimizations. In addition, you need to master the concepts of Spark RDD, data frame, data sets, and dstream. RDD is a fault-tolerant collection of elements that can be operated on in parallel. Data frame is used for processing of large amounts of structured data based on RDD. Dataset. It allows performing an operation on serialized data and improving memory use. Thus, it allows on-demand access to individual attributes without deserializing the entire object. Dstream is represented by a continuous series of RDDs. So that's all. Thanks for your listening. See you next time.